Meow. Meow, 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 meow. Meow. Hello, guys, and welcome back to a physics video by me. We're going to be doing electricity today. How do I delete this? This was my intro. I hope you liked it. Okay, so let's get started. So we're going to be doing some general AS level electricity. This involves internal resistance, EMF, voltage. There is also the formulas of, okay, anyway, let me get into it. Here are some formulas you need to know before you start. So these are some basic ones. I don't know if they're given. They should be given, but anyway, remember them. V voltage equals the current. The voltage drop across a component equals the current in the component and the resistance of the component. Okay, the voltage in the circuit, the total voltage drop across the circuit is the internal voltage or the EMF, okay, minus the voltage drop internally, that is due to this small r. What that small r is internal resistance. Okay, so you're not getting all of the energy you supplied to the cell, if that makes sense, because the cell also has some internal resistance. Let's say this is your cell and you are giving it an EMF of 9 volts, but because of that little bit of internal resistance that it needs to overcome, you're only getting an output which is actually used in the circuit of maybe 8 volts. I hope that makes sense. Yep, there is also the formula for EMF, which equals the current into R plus R. This is the resistance across the circuit. This is the internal resistance. To find this, you might need to add the reciprocal and then reciprocal again, based on whether it is in series or parallel. This is basically the effective resistance of the whole circuit. Anyway, let's get started. So, oh yes, also there is this I equals NAVQ, where Q is the charge of a particle, 1.6 into 10 to the power 19 or minus 19, based on whether it's an electron or proton. V is the drift velocity of the electrons. A is the cross-sectional area of the wire it's going through. N is the number density of electrons, and I is the current. Okay, let's get started. The cell has an internal resistance. So this is our cell, and this is an internal resistance. Okay, the current in the cell is 0.8 amps. Wire X, which is this wire, has length 3 meter, cross sectional area 1.3 into 10 to the power my blah blah blah. Just kidding, don't say blah blah blah. And resistance in this. Alright, very cool. Calculate the charge passing through the cell in a time of 7.5 minutes. So the formula of charge, which is in coulombs or amps second, if you want to say in base units, equals current into time. So we have current that is in this wire, that is 0.8 into the time. Right now, my guess is, why is this 2 marks? Right, this seems pretty straightforward. That's because they want you to convert time from minutes to seconds, because the base is in amps second, the base unit, right? Amps and seconds. You need this in seconds, so we can say 7.5 into 60. So let me plug that in my calculator. That gives us a value of 360 amps second, but we should say coulombs because that's the SI unit for charge. So we're going to say 360 coulombs. Moving on. Calculate the percentage efficiency with which the cell supplies power to wire X. So why did I do that? Okay, so this is our cell, right? Now the percentage efficiency of power. So let's start off by securing some marks. Always write the formula. This could give you a mark if you get the question wrong. So power is equal to current into voltage. Now current is constant everywhere. Since this is in series, current is constant here, 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 here. You get my gist. Even within the cell, current is constant. But what is not constant is voltage. Across this component, there is a voltage, which is our output power. And what is being lost? The voltage across this component. Our input power is the actual voltage that has been supplied to the whole circuit. But because of this internal resistance within the cell, it is eating up a bit of our EMF. Okay, so the EMF is eaten up. There's a small voltage drop within the cell because of the resistance. Remember, IR, right? The resistance in the cell, which gives us a voltage drop. So there's less voltage for the rest of the guys. Does that make sense? So we can say power input divided by power output divided by power input into 100 is our efficiency, right? So let's start by calculating the power input. So power input equals the total current, the current into the total voltage. Is the EMF given? Yes. So they've already told us that the EMF is 0.48 volts. So we can just go ahead and plug that right in. So 0.48 volts, that's our EMF. That means that's how much is being supplied to the cell. But the cell doesn't use that much. So how do we find the voltage across this cell? So let me erase this. How do we find the voltage that the cell has? We can find that using internal resistance, right? V equals IR. But we don't know R. We don't know R and we don't care about R. We can find the voltage that is left for the rest of this cell by finding the sum of voltage drops, right? Let's say 10 volts is dropped here, right? That doesn't make sense, but let's just say 10 volts are dropped here. That means that there is 10 volts across this as well, because the voltage difference across any 2 points is the same. Does that make sense? The voltage drop across here is the same as the voltage drop across here, meaning let's write this. So the voltage or the power output equals 0.8, which is our I, into V. What's V? What is the V that's being output? So we can find that by calculating the sum of the voltage drops. There's only one component that actually eats up voltage here, which is our wire, which has resistance. Resistance eats up voltage, which is why our internal resistance reduces the EMF to give us voltage. Okay, I hope you have a clear understanding of these concepts. It is very important to do so. Now let's find the voltage drop across this wire. V equals IR. V, which we want to find, equals I 0.8 into R 0.4. So now that we know this value, we can go ahead and plug it right into this. So that gives us a value of 0.32. That means 0.32 volts are being dropped across this circuit, meaning that whatever's left, this is going from this to this because of this internal resistance. Now we can find the internal resistance because we know these two and we have all these formulas, but we don't need the internal resistance. So let's move on. So now let's plug in the voltage 0.32 and let's find the power, the efficiency. So power output, when you divide these two, these get cancelled, giving us, this is supposed to be on the top, sorry. So 0.32 divided by 0.48, the I and the I get cancelled. So let's see what that is. So that is 67%. Okay, so our efficiency is 67%. Make sure to show your working so you can secure the maximum amount of marks. Moving on, there are 33.2 into free electrons contained in the volume of wire X. For wire X, calculate the number density N of the free electrons. Now there is a formula, but this is think of it logically, okay? Density, when we look at it in terms of mass, it is mass by volume, right? They want number density, so it's the number of electrons by the volume of the thing, right, of the wire. So that will give us density. So there are these many electrons, right, and this much volume. So we're going to start off by saying 3.2 into 10 to the power 22 divided by the volume. What's the volume? Length of the wire, cross-sectional area. If you take the cross-sectional area and multiply it the amount of times you have the length, you get the volume of the wire. That was a terrible drawing. Please don't unsubscribe. I got 5 subscribers. I'm in a good mood right now. Okay. So that will be, the volume will be 3 into 1.3 into 10 to the power minus 7. Let me plug that in the calculator. Bear with me. 3 into 1.3 into 10 to the power minus 7, which gives us a value of 8.2 into 10 to the power 28. So that is our number density. That means that's how many electrons are there per unit volume. Now, the average drift speed of the free electrons. So we have this, right? This is like a sub question, if you will. So I equals NAVQ. The current we know is 0.8 equals N, which we just found. Let's bring N to the denominator because we are making V the subject here. 8.2 into 10 to the power 28 into, let's bring Q to the denominator, 1.6 into 10 to the power minus 19, because this is the charge of an electron, Q is charge, into, lastly, we have to bring A to the denominator. So let's do that. What is A? A is the cross-sectional area. So 1.3 into 10 to the power minus 7. Oh boy, this is a lot of work. Equals V. That gives us a value of, oh, you have to really bear with me now, 0.8 divided by 8.2 into 10 to the power 28 into 1.6 into 10 to the power minus 19. If you're not skipping the video here, I think you really like the sound of my voice. All right, that gives us a value of 4.6 into 10 to the power minus 4 meters per second. All right, lastly we have okay, no, let's say 4.7, we're rounding up. Okay, this is our last part, and this is a bit of a theory question, I guess. So now we say a wire Y has the same cross-sectional area as wire X and is made of the same metal All right, wire Y is longer than wire X. So everything about wire Y is constant except the fact that wire Y is longer. So wire Y is longer than wire X. Wire X in the circuit is now replaced by wire Y. Assume that Y has the same temperature. So that now resistance depends on temperature, which is constant, same as wire X basically. It also depends on cross-sectional area, which is the same. So the only thing that changes where resistance is dependent is the length. So resistance is proportional to the length, meaning if the length increases, so does the resistance. So we know that the resistance for wire Y is greater than X. You need to establish this very clearly so you can move on to the next step and deduce what they want you to deduce. State and explain whether the average drift speed of the free electrons in wire Y is greater than, less than, or same as, or less. Yeah, you get the idea. So we have to compare the average drift speed relative to X. So formula, I equals NAVQ. So we know that the resistance of Y is more, right? So this has more resistance. Because of that, this current decreases, right? So right off the bat, we can say that I decreases. Now you're going to have to write this, but I'm not writing it because I'm lazy, and I'm going to show you, and you have to kind of, you should be able, from this, you should write something, all right? So I decreases. Now, let's make V the subject so we have a clearer understanding. N is constant, the cross-sectional area is constant, charge Q is constant, right? So I decreases and the resistance increases. And since, where is V? No, sorry, N increases because the wire is longer, so it has more volume, right? So there's more volume, so N increases. Well, we don't know how many electrons are in, but this is a lot of, these are maybe a bit too many variables to consider, but I don't think this is needed. You need to mention about N, but even with N increasing, it gives us the same result, which is that the drift speed decreases, right? Overall, the drift speed decreases because I decreases, right? So you're going to start off by saying resistance increases, which leads to current decreasing. And since I and V are directly proportionate, V decreases. So resultantly, V decreases in the end. All right. Yeah, theory in electricity is always a bit tricky, but if you are able to define clearly and work your way, you can get it. Thank you for this class. 5 subs is a great thing, and I'll see you guys in the next one. Bye.